Hello and welcome back. In today's video, what we are going to learn is classification of fluid flow. Now there are various types of classification that we use in fluid mechanics. One is viscous versus inviscid flow. Then we have laminar versus turbulent flow. We have compressible versus incompressible flow, internal versus external flow, one-dimensional, two-dimensional, and three-dimensional flows, rotational and irrotational flows, natural versus forced flows, steady versus unsteady flows. Now we will not cover all of these types in this video. We'll only start with the viscous versus inviscid flow in this particular video. Now let's start with viscous versus inviscid flow. Now in order to understand this flow, we'll take an example. Suppose a ball or a football, say, it is moving through still air. Now this is one type of flow that we are considering here. It is moving in still air. Now we may think that if air is still, how will this be fluid flow? Now, as I have already taught in the previous videos, that whether a fluid is at rest and an object and a body is moving through it, that's a fluid flow problem, because motion is relative. So that would mean a ball is at rest and the flow is moving in the opposite direction. So we'll take this example. Now if this ball is suppose ascending or descending in this motion, now we want to know what are the various forces that are affecting here, that are acting here. First of all, we have elevation change, so we have gravity. Then we have drag force. Now we have drag force. Now to make this explanation simple, we will remove this gravitational effect. Suppose this ball is moving from this place to this place horizontally, so there's no elevation change, so we'll remove the effect of gravity. So what we have here is this flow field is dominated by drag force. But drag force itself is made of two types of drag forces. One due to normal stress acting, which is the pressure. In case of fluids, we call this pressure drag. And another is the shear stress acting. Another shear stress acting at the interaction between the fluid and the body surface. We call this friction drag or secant friction drag. Now the question is, we want to know whether this particular flow system, flow field, is dominated by pressure drag, or whether it is dominated by friction drag, or whether it is dominated by both. Now that is where the concept of viscous versus inviscid flow come in. Now if a flow field is dominated by friction drag, now if a flow field is dominated by friction drag, we call this viscous flow. Now if a flow field is dominated by pressure drag and the friction drag is negligible, so we call it inviscid flow. Now now we have the basic idea what viscous and inviscid flows are. Now how do we decide whether a given flow is viscous or inviscid? Now one may think, since viscous flows are something that have viscosity, and inviscid flow is something that does not have any viscosity, that's totally wrong, because in practice all fluids have some viscosity, so they are viscous. But we differentiate a particular flow field. It will have some regions that have higher viscosity, or that will be viscous-dominated, and there will be other regions which will not be viscous-dominated, where effect of viscosity will be negligible. Now first thing that comes in mind in this case is, suppose if we have a fluid that has higher viscosity, that will be viscous, and if a fluid has lower viscosity, very low viscosity, that will be inviscid. But this notion is totally wrong. For that, I will give an example that will explain why this is wrong. I will take an example where I will keep the fluid same. If the fluid is same, viscosity is same. If the viscosity is same, the fluid flow will still be different. One will be viscous case and one will be inviscid case. So that will take us out of this notion that if a fluid has higher viscosity, that will be viscous, and lower viscosity, that will be inviscid. That's very important for that. So we'll take two examples. In both examples, what we'll take is, we will take air as a fluid, so viscosity is same and other fluid properties are also same. But still we will have one case as viscosity dominated, and other case will be viscosity where viscosity is negligible. Suppose we have, this is air in both the cases, still air. Air, so viscosity is some mu, and here air, viscosity is the same mu. So according to the notion that higher viscosity, lower viscosity, viscous, inviscid, so according to that notion, both these flow fields should be viscous, either viscous or inviscid, but they will be different. So in one case we'll take a football, and that is kicked at very high speed, and another case we'll take a small dust particle that follows under the action of gravity, that falls down. So velocity is very low and size is small. Size is very small and size is large. Size is large. Fluid properties are same, density is same, since here it is air and here it is air as well. Now in this case, the pressure drag, if we do experimentation, we'll find that here the pressure drag is dominant, and here friction drag is dominant. Because of this large speed and this larger size, the pressure will build up on this side if the air is flowing in this side, in this direction, or ball is moving in the opposite direction. So here will be pressure build up, here will be pressure low, so there will be drag in this direction, which will be the drag due to pressure difference, pressure drag. Here size is very small, speed is low, there will not be significant pressure drag across this particle. So whatever drag this particle feels is due to the friction, internal friction of the fluid, which will be the friction drag. So we have air here, we have air here, but this flow system is pressure drag dominated and this flow system is friction drag dominated. So we can say that this is viscous flow and this can be regarded as inviscid, although both have same fluids and same viscosity. That's why I said higher viscosity fluids are viscous, lower viscosity fluids are inviscid. That's not the concept. The concept involves whether a flow is viscous or inviscid. This concept involves all the three factors. It involves size of the object, it involves the fluid properties, viscosity, density as well, of course, and it involves speed as well, because that is why whether a flow is viscous or inviscid, that will be determined by the whole flow system, not just the fluid, whole flow system, and whether it is viscous or inviscid. Now from this discussion we get we say that how do we decide that this flow system or a given flow system is viscous or inviscid? That will be decided by all these parameters. So experimentally it is found that when a fluid is viscous dominated, or whether when a fluid is pressure dominated, what we see that here velocity is high. Velocity is high. So higher velocity takes us towards inviscid flow, larger size. So for the size we take length, it's called characteristic length for the size. And if a fluid has higher viscosity, if a fluid has higher density, it takes us towards being inviscid, pressure domination, and of course lower viscosity as well. So now if a flow will be inviscid, so the viscous domination will be less, frictional effects, friction drag will be negligible, and pressure drag will be significant. If the viscosity is high viscosity fluid is there, velocity is very high, body size is large, but the viscosity is low. So these together, this flow system spits out these four parameters, which collectively define whether a flow is inviscid or whether it is viscous. Now these four are combined and we called it Reynolds number, a dimensional parameter. We call it Reynolds number. So this Reynolds number is very important in deciding whether a flow is viscous or inviscid. Now how do we, we have a flow system in front of us, we have body, we can determine what is L, at what speed is it moving, what is the fluid, so what are the fluid properties, and we can calculate the Reynolds number for a given flow system. Means not just the fluid, but the body size, speed, and all that flow system. After calculating the value of Reynolds number, how do we decide that in this particular case whether we have frictional effects are significant or frictional effects are not significant? And for that we have a rough value. There is not a sure boundary that decides. There is a rough value we can remember is if Reynolds number is much greater than 10 to the power 3, much greater than 1000, so the flow has negligible friction. So negligible friction means it is inviscid. And if Reynolds number is much lesser than 1000, then friction is dominating, so significant friction. Or flow is dominated by friction, and in this case flow is not dominated by friction, but it is dominated by velocity thing called inertia. It is dominated by inertia. So dominated by viscosity, you have viscous effects, you have viscous forces, and here flow is dominated by inertia, inertial forces. So now we know what is viscous flow and what is inviscid flow, and this is not basically related to just fluid but the entire flow system. And to decide whether it is viscous or inviscid, we use a parameter called Reynolds number, which consists of 4 parameters. And if it is much greater than 1000, then inertia effects dominate, and if it is not dominated by viscous forces. And if it is much lesser than 1000, the flow is dominated by viscosity. So this is viscous versus inviscid flow field. Now there is very important thing that we have to understand here after this is that there is not a single flow field which is either fully inviscid or fully viscous. And inviscid, actually theoretically inviscid means viscosity is 0, and we know that in real flow viscosity is never 0. And since we got this flow field as inviscid, and it doesn't mean the viscosity is 0, there is viscosity of course, but there are other parameters which dominate that suppress the effect of viscosity and make the effect of pressure drag more. That's why this becomes the inviscid flow field, but mu is never 0. This is very important. This is why when we talk about viscous versus inviscid or other laminar versus turbulent, compressible versus incompressible, we should use regions of flow, because a single flow region, let me erase this first. For example, if this is a ball and air is moving over it, and air is flowing over it. Now if we talk about this region of flow, if we talk about suppose this region of flow which is away from the surface of the ball, this can be recorded as inviscid, provided the fluid is not having high viscosity in this particular case, because we are removing the effect of the ball, the size L effect. We are taking away that L effect and all that. So this region away from the ball, this is inviscid region of flow. But the region near the surface of the wall or the region behind the wall, these are viscous region of flow. So a single flow system can have two different regions. One where viscous effects can be neglected, inviscid regions of flow, and others where viscous effects cannot be neglected, they are dominant. We call them viscous regions of flow. That's why we should always talk about regions of flow. There is a flow field, and it has some parts where viscous effects can be neglected. So we call them those regions inviscid regions of flow. So we should always talk about regions of flow: inviscid region of flow, viscous region of flow. That's very important. Like compressible regions of flow, incompressible region of flow, laminar region, turbulent region, and all that. Laminar regions of flow, turbulent regions of flow. This is a better terminology than saying this flow is viscous or this flow is inviscid, because no flow is inviscid. Inviscid means completely inviscid, which means viscosity is zero, and it is never zero. It will always have some non-zero value. So we talk about regions of flow. So this was all about today's video. So we started with the various classifications, but we only touched the first classification and gave some important concept related to viscous and inviscid regions of flow, and defined a parameter, a dimensionless number called Reynolds number. Thank you.